All right. Welcome to the second C++ meetup at Woven Planet. We're thrilled to see the continued momentum for these events. Our goal is to really rally and support the C++ community in Tokyo, Japan, and obviously the world. And we're thrilled that all of you made the time to come be here with us today. So thank you very much. We're happy to see you here. Tonight's topic is C++ and security. We have two amazing panelists joining us today who will introduce themselves in just a moment. But for everyone in the audience today, whether this is your first one here or you're returning from the one in November, I'd like to remind you that this really is your opportunity to interact and ask them all the questions you have on C++ and its intersection with security. So please, I know it's kind of tough to walk up in front of everybody and ask a question, but we're all very nice. There are microphones in the middle. I will start off with a couple questions we have selected from pre-submitted ones from the audience. But please, whatever you're interested in asking, line up in the microphones in the middle and ask your question. We are really excited to have a discussion with you today. そして日本人の皆さん、今日はここまで来ていただいてありがとうございます。同時通訳したリプな2人もいますので、ぜひ質問を聞くときに英語でも日本語でもどちらでも構いません。真ん中のマイクロフォンに進んでいただいて、並んで自分の番になったらぜひ何でも聞いてください。とても楽しみにしています。ありがとうございます。One final thing before we get started, please, to help make our wonderful translator lives easier, please speak slowly. You'll make them very happy. And you'll also make me very happy as well. Thank you so much. I'd love to turn it over to our two amazing panelists now. JF, would you mind introducing yourself first?
Yeah, thank you. So I'm Jeff Bastien, I'm Chief Architect at Woven Planet, and I also chair the evolution of the C++ programming language as part of the ISO committee. And I've done a decent amount of security work in the past, primarily on Clang and LLVM.
Thank you very much. Caleb.
Sure. So my name is Caleb. I am a security engineer at Woven Planet. I work primarily on a product known as Arena OS. I am part of cybersecurity, and we have a lot of colleagues of mine in the audience today. Prior to Woven Planet, I worked at Microsoft on Windows doing security engineering.
Thank you very much. OK, we have just under an hour for discussion, so I would like to jump right into it. Let me start off with a couple questions we've selected. So if I call your name, if you could come up and give us your question, that would be wonderful. Are you here today? Thank you.
Yeah, so it's been a little while since I asked the question, so I hope I remember it correctly. But my question was that roughly in security issues, I am quite concerned about my dependencies. And yet, in C++, there is no standard way to manage dependencies. So basically, what are your thoughts on dependency management? And maybe do you have preferred tools on and practices around dependencies?
Yeah. So it's a problem that we're very concerned about of when you have very big code bases that are often created by different teams. They end up using a variety of sources for code, some of it open source, some of it closed source, mixing it together, and ideally managing their dependencies internally, but across those teams, the management is different, right? So what we're trying to do, I think as an industry, right, not just for C++, but at large, is to figure out how to manage repositories individually and their versions, right, to be able to identify any vulnerabilities or safety issues or things like that and different ones. And I think companies like GitHub do good work there in trying to help manage this, and they're not the only ones. And then on top of this type of work, I think within C++, you want to manage the dependencies, right? So I think in small projects, something like CMake is easy to use. It's easy to declare your dependencies and do things. Things like Git modules allow you to manage some dependencies okay. But I think at a fairly large scale, solutions like Bazel allow you to manage them better. It gives you more. It's kind of built into Bazel that's kind of how you manage things through different dependencies and repositories. And then the key, I think, is to have visibility into all of the repositories that are used to create like a software bill of material for the final build product, where you can see not just the software you built that ended up into your executables, but also to be able to see all of the software that went into creating that artifact, right? So if you look at the old Turing Award Trusting Trust lecture, right? Like you want to have the compiler be trusted, and you want to have the tool chain and everything else that went into it be trusted, not just the source code itself, right? Because if you want to do a supply chain attack, right? If you're malicious, you wouldn't necessarily attack the source code itself that goes into, say, a vehicle or any consumer product. You might attack the tools, right? So I think having full dependency on all of the software, the open source that they use, the versions, and visibility into that is solved by an SBOM, but also the whole supply chain that goes into it, right?
Yeah, I guess I'd second JF's comments. I might add that I think that there's kind of, this is almost a chicken and the egg problem, right? So you need a way to have auditing or visibility after the fact. That's what SBOM provides, to know what is in your software. And then you want to have a way to guarantee prior to conducting a build, right? So that your build system doesn't get compromised, that the software that you're building is actually what you want it to be, right? And so having trusted sources, having defined locations where you get your dependencies from, say a particular organization, or building things from source, or say relying on Bazel to produce hermetic builds, are practices that must be implemented in the engineering organization to solve this problem. As far as I know, JF could correct me if I'm wrong here, the language doesn't have any built-in mechanism that solves this problem at this time. Other languages obviously do have some things in this area, like obviously Go has like Go modules and Go get, and certain things are adjusted in a particular way, but C++ does not, right? Similarly, the tooling also doesn't, right? So it's very important that you have a very well-controlled tool chain, that you know what you're using, you know what properties it provides, and then you make sure that your builds are at a minimum reproducible. You want quite a bit more, to be frank. You want things to be signed, you want things to be authenticated. These are all initiatives that we have different components and pieces on going on internally at Woven Planet. So we do take this stuff very seriously, right? For the vehicle, right, we have to know everything that goes on it, obviously. And for any car in the world, you want this because you want to be able to guarantee that the car is safe. And one of the ways in which you make sure that something is safe is you have to be able to account for any component that is part of it, right? So that's something that we have to do. But the solution to that is largely by using tooling and other things that are outside of the language that we work on. Thank you.
Yeah, one thing I want to add is in the C++, the language itself and the standard don't do this today, but people in the committee are aware that this is a problem. And there's a subgroup called the tooling subgroup looking at not just this specific issue, but a variety of connected issues. One of the things to keep in mind, though, is C++ was created without such an ecosystem, right? So you can't really come in and say, this is now the only way to manage dependencies, right? As a committee, what we're trying to do is to say, well, this is a problem, and all of the tools trying to solve it are doing this common thing. And so there's vendors in the committee like, Microsoft has a big presence. The LLVM developers from a variety of companies have a big presence. There's a few people who work for Kitware on CMake and similar kind of tools. They've come together in this tooling group to identify what they think are the salient things that they're all doing, where they could benefit from one separate standard. And so the committee is not going to say, as part of ISO C++, this is what you have to do. But they're going to have, I think, a separate document, like a technical report probably, or something like that. Like some ISO has separate types of documents to do that type of thing, that tools can adhere to say, well, we expect or expose these particular things, right? But again, the difficulty is going to be, well, do you force people to use modules to solve some of those issues? With C++ modules, some of them are easier to fix, whereas with textual inclusion, it might be a bit trickier. Like your abstraction level when you're doing textual inclusion doesn't really, like, you need a build system to do textual inclusion, but so that the textual inclusion can't really say, and here are my dependencies, right? Whereas within modules, it's kind of more hermetic, it's kind of built in. So I think they're trying to navigate the more legacy as well as the diversity of tools that do this to bring them together and help all of those tools solve that problem individually much more easily. Because I think that's one of the problems C++ has had for a very long time. Overall, is it's very hard to tool as a language. And so that as tooling becomes more mature and there's more kind of organized way to fix those problems, I think it simplifies things. And then it's up to each vendor, and a lot of the vendors are open source, end up creating solutions for supply chain security, but also other things like faster builds or easier to make them reproducible and things like that. So I think it solves multiple issues at the same time.
This is like what I'd term, like, I guess, like a big rocks problem, right? And C++ being a very mature and diverse ecosystem is going to have challenges like this that are going to be harder to solve over time, right? There's not going to be a one-size-fits-all. The language isn't new. It's been around for a long time. It has a very established community base. It has developers and tool chains that are locked to specific versions, right? So automotive being an example where your tool chain is often pegged to a particular version of C++, and you may not get the latest features. You may not get the latest tooling. You may not get some of the latest and greatest protections that you have for systems that you will produce or you will be manufacturing for maybe the next 5 to 10 years. Like in the aerospace industry, for example, you will have embedded systems that are used to manufacture planes, and they will have a lifespan of, say, 30 years, right? In which they will be supported. Likewise, automotive, we have a long support cycle. And so some of these solutions, they may come within the next few years, but for adoption in the industry, it will take a long time, right? And that's kind of why I look at it as a big rocks supply chain. That's a huge initiative, right? I see there are probably several other issues in this space, like how do you make, say, C++ memory safe? That's like another, what I would term, big rock to solve, right? Because you have a lot of code base out there, and memory safety bugs are often very serious ones when they're encountered, right? And so people are working on this, and this isn't the best answer. There will be some kind of solution eventually, but it will take a while, and then you will have adoption afterwards before the solution comes down. And so in the meantime, we at Woven Planet obviously have stopgaps in place in order to address this, right? But it is something we care about.
Thank you very much. Yeah, and I just want to echo, but thank Jeff particularly, because my follow-up was about how can we make it easy, basically, for people to get started. So I'm really looking forward to new tools. Thank you.
Thank you so much, and thank you for helping us break the ice in the questions. Would anyone like to hop up and approach the microphone and ask their question?
You mentioned memory safety at some point. I'm curious, what are your thoughts on Rust and its ability not to replace C++ in the midterm future, but to coexist with it?
I guess I'll start with this one. So, I mean, I like Rust as a programming language. There are specific places within Windows where Rust is employed, particularly within the hypervisor. We have integrated Rust in to the kernel for certain specific areas where we need memory safety guarantees, right? So I think that C++ and Rust very much can coexist. I guess my statement there would be that Rust use needs to be done strategically, right? In terms of maturity, and this is my personal opinion, C++ is a lot more mature, right? Obviously, C++ meets certain safety standards that are out there, and like physical safety standards, right? Because that's something that we deal with in automotive that Rust may meet or may qualify at the same level of someday, right? But for the moment, there are different levels of service there, right? And so I have no objections to Rust being used in specific places, right? It's, I firmly believe in using the right tool for the job, right? That's a very security engineer perspective. Like, you use what needs to solve the problem and not anything else, right? But in many cases, C++ remains the best tool for the job, right? And there are things that we can do in ways in which we can write the code, right? And then analyzers that we can run on top of it that can provide what I would consider an adequate level of memory safety for where we use C++. Now, that's my opinion, and I'm not interested in necessarily debating it.
Yeah, and I think as a basic interop level, what makes it easy for two languages to interop is when they have a nice set of APIs to talk to each other. And if you've programmed in C++, trying to interop with C, I wouldn't say the extern C or just textual .h inclusion of code that happens to be valid C and C++ is a nice way to interop, right? But that's what we have as our common language between, say, C and C++. And with a variety of other languages, the C level of compat is what you end up having, right? So I think if you look at I'll do a comparison of the interop that you might have between Objective-C and Swift. That one's amazing, right? And Swift is meant to be a language that migrates you from Objective-C to Swift, and the interop between the two is just really, really seamless in interesting ways. And I think the interop between C++ and any other language is really shackled, like really hampered if it's a C-based interop, right? If you have to take your C++ code, your class, just boil it down to a struct or a pointer and then create C interfaces with pseudo namespaces that look like that. And so I think if you're trying to create a space where within a code base or a variety of code bases, you can interop between C++ and any other language, not just necessarily Rust, but any other one, then having a real native way to go both directions is really critical. It can still be a subset of C++ and a subset of Rust or whatever else that you expose, but I think that's a critical aspect of what you're trying to do. And then if you have there's resources around this as well, right? You can't just present resources as pointers and say, you figure it out, because that ends up being buggy, right? And there's guarantees around resources, right? So if you say in Rust, you have the borrow checker and you give something to C++ and you just have to say unsafe, it's not great, right? The same way, I remember when JavaScript and Dart were trying to interoperate, one of the big issues you ran into so Dart, the programming language that was built as part of Chromium, right? JavaScript has a garbage collector. Dart has a garbage collector. If you want to share objects, that becomes tricky, right? It's a shared resource, but the garbage collectors initially didn't have visibility into each other's resource usage, and so you had to do weird stuff to be able to have the other one know that you were holding on to big stuff, and so it was worth garbage collecting or whatever else. And so that's the type of issue you run into when you have these interfaces. It's not just, can I call your code, give you a data structure? You want to have ergonomics there, but it's also, can my model be exposed in yours in terms of resource ownership and in terms of invariance that I provide? And I think that's one of the hardest parts. So if you want to try to solve the general problem, then you have to solve really, really hard problems of how do you do general resources, all of them. How do I do general invariance? All of them. But as an adopter of something like this, right? If I own the code base, I can choose my boundaries in a smart way to say, these resources are the only ones that matters at this boundary, or these invariants are the only ones that matter at that boundary, right? So one of the things that I think gRPC really revolutionized was this is how you communicate, right? With protobuf and gRPC, this is the thing we exchange, and it's just bytes. There's a structure to it, but you can represent it in different languages, and it kind of just works. And so there's no resources attached to that in a lot of cases, right? And so if you wanted to interop between, say, Rust and C++, and you wanted to do it in a way that doesn't have to care about threads, doesn't have to care about file system handles, about any type of thing like that, and you did it through a interface description language that had a clear model and value passing, then that works well, right? So approaching the general problem, I think, is hard to fix, but approaching a specific subset of it, you can have nice solutions as well. Now, whether that works for your problem space or not depends, right? So I think that's the way I would approach it if I were not in control of any language or anything, but I'm in control of my specific code bases in their ecosystem. I would, define interfaces pretty nicely and then try to not have to solve the hard problems, basically.
Thank you so much. That was a great question. Really appreciate it. Would anyone else like to step up and ask their question? Please. You can just hop up and walk to the mics at any time.
すいません、日本語で質問をさせてください。言語のエコシステムにラストのカーゴとかノードのモジュールみたいなものがあるとすごい便利だなと思っていて、で、特にその C++ コミュニティを発展させていくっていう目的でもそういうものがあるといろんなライブラリとかを組み合わせてプログラムが作りやすくなってすごいいいなと思ってるんですけども、なんか標準化委員会でそのような取り組みとかがあるのかどうかっていうところと、でなんかツーリングスタディグループとかあると思うんですけど、そこら辺でどういったものをこのなんかカーゴとかノードモジュールみたいなものとかもなんか含めてなんか目指していたりするのかっていうところを聞きたいです。
ありがとうございます。
Yeah, thank you. So I think within the tooling study group, people are very aware of how cargo works and how node modules work, and what they've done really well. Right? And I think there's good efforts. Like I think Microsoft does, for example, VC package that tries to do something similar that within a particular ecosystem works well. I think Conan is another example that works well, right? Within C++ areas. The problem again is it's difficult to have one solution for everyone. Right, so I think that's something that the tooling study group is looking at. They put out a document. If you search for like ISO CPP SG15 tooling group, they have a proposed charter of what it is that they're going to look at. SG15 is the unrecognizable name for the subgroup, and they have a document that explains what they're targeting to do specifically for package management and things like that. But again, they want to solve the problems that group can solve while helping entities like VC Package or Conan solve more specific issues, right? But I think one of the things you want to be able to do is have a description of dependencies, description of build settings, and dependencies outside your code base as well as within your code base, and then any kind of build setting or build steps that you need to have. And I think that's one of the issues that exists inside of C++ that Node doesn't really have, right? Cargo has that same issue, but has solved it with a uniform way to do it. And VC Package, I think they put a lot of effort towards doing that work for individual code bases, or Linux distributions do that as well. It's a lot of work, and so I think they figured out an interesting list of what it is that you would need to do to make that work easier for packages to then subscribe. But what I've observed is open source code bases sometimes it's not a job pretty often. Running open source is a lot of work, and it's a thankless job. And so I think for open source maintainers to then come and adopt a new thing, it's kind of annoying sometimes, right? And I understand why. Like they're not being paid for this fairly often, and they're being asked to support one thing and another and another. So that makes the adoption really hard, right? So it's basically if C++ were created today, it would obviously have a package manager. But adding one now, I'm hopeful will happen to have at least the basic tools to help everyone solve that issue. But there's a lot to do. It's difficult. So I think it'll take a bit amount of time.
So if I can ask you a question on this, and this is something that you would know from your work on the standards committee, like how long does it take for a feature to get adopted, right? So something gets published, it goes into mainstream, and then you'd say 50% of code bases now take advantage of this. Let's pick something simple, like constant expression.
Yeah. Well, that's tricky. So it depends if you're talking of language or library features.
Okay.
Library features are much easier because usually when you standardize a library feature, it's already available separately as a few implementations. Right? So one example is the expected type that I helped standardize. It's just a tuple with two fields, an expected value and an error value. Fairly simple. It's like a vocabulary type. That's existed in a variety of code bases for a long time. Coming up with the final API, it took a while. I think it took like 6-7 years to get it there for reasons. There's reasons why it took a while. But it's been available for a long time. So the adoption has been there for a long time. Now, if you look at language features, you can't use it unless it exists in a compiler. Most compilers nowadays don't want to ship a feature unless it's actually standardized or unless there's a big scary flag that says don't use this or experimental or something like this. So if you look at something like Constexpr, I think it takes quite a while, and it's a fairly niche solution initially because it doesn't do much. The initial Constexpr doesn't do much, but the newer ones do a lot more work, right? So I think people, as they discover, hey, we have this thing, we're going to start using it, they start using it a lot more because it's more powerful. One like personal example is, in the 2000s, I used to program in C++ 03. Right? And then I moved to a company in 2009 that I only did C code for a while. And C++ 11 happened during that time. And then I moved to a company that didn't just do C code, but did C++ again. And I discovered lambdas, right? A few years after they were like officially usable. And for me, it was like, oh, wow, you can use lambdas. This is beautiful. And then I moved somewhere else that had C++ 14, and then I discovered auto lambdas, right? And that was like 2 years after auto lambdas were standardized. And so I think part of the issue is not just when is it available and I can try it out for fun, but when is it available, when does my project use that language standard, right? And I think something like in automotive, we're a bit slower to adopt new standards because there's all these tools that go around it to help you prove safety of a variety of things or make a safety case for things. So I think that's something that makes it longer to get those features available.
Yeah, so the reason why I picked on that was to give an example of, say, Constexpr came out in C++ 11, and I'm aware of people that are still adopting it, right? And that's a language feature. And I'm assuming that tools take similarly a long amount of time.
Yeah.
And so when there is a solution for this, I think we're looking at probably a 10 to 15-year time before this will actually be a solvable problem. Because this is something that people ask for all the time. And I actually have read that standards group, their paper on it. And so I'm kind of aware of what's going on. It's just I think that it will be many years before we have something that I think is wide because of how large and diverse the ecosystem is.
Yeah. But I think when there's demand for something, the tools around them move faster, right? So, and it's a bit of a chicken and egg. If the thing's not available, then tooling people don't support it. And so because tooling people don't support it, the demand's not there. So that's a bit tricky as well, right? Like, I think I'm hopeful that you're wrong, that the tooling standard will propagate faster. I'll admit that you're right if it turns out you are, but I hope you're wrong.
We'll have a bet. I'll buy a beer if I lose.
Sounds good. Yeah, thank you.
Thank you.
Thank you very much. That was an amazing question. Really appreciate it. Who else would like to ask a question for our panelists today?
Yeah, go for it.
Okay, my first question was really generic on Rust, so let me ask another question that was asked previously. I would just like to bounce off the previous thing you discussed about adoption. Specifically, JF, you started to mention that because of safety, things take, if I quote you, a bit more time in automotive, I would say that this quotation, a bit more time, is not an exaggeration, it's the opposite. Like, usually we speak about a decade. I can give a few examples. For example, if we look at the safety standard, safety coding standard like MISRA, the first version of Inspira C++ published in 2008 was for C++ 2003. This one was replaced by AutoZAR in 2017. So like until 2017, the only safety standard for C++ was 2003. Right now, the only standard that we have is AutoZAR, which is C++ 2014. And the C++ is going to publish C++ 2023 this year. Like, we are 1 decade behind. With the automotive field trying to solve like modern problem, like AI, automation, etc., we have a lot of appetite for modern solution, but we are still living in the past because of the tooling, etc. So I have a kind of open question of like how to balance, how to do modern things with when your tooling is 1 decade behind. Yeah, thank you.
And I think you're touching a bit on a few things. One of them is, I think, in a safety industry, there's a few ways that you can convince yourself that stuff is safer. Right? One of them is you decide on things, you don't change them, and then you study really hard, put a lot of effort to making sure it's good, and then that's what you have. And then when you want to do something again, you decide on a new thing, you code around it, you study it really hard, and you make sure it's good. Right? That's by and large what most safety-related industries do. What some more security-minded industries do is they evolve over time, right? And they're not always at the leading edge, right? But they try to follow fast, and they invest instead in evolving code bases, investing in it, and creating quality in that inherent code base by having it embrace tools that change over time. Because tools changing over time can give you certain quality attributes in terms of security or safety or so on. The issue is in safety environments, it's not really well known how to do this, right? It's not something that people have really tried out. I think it's something important to try out. That's one aspect of your question, I think. The other one is a bit of a tragedy of the commons, right? Like, when you look at standards, when you look at tools and so on, you wish someone would do it, but you're someone and you don't do it fairly often, right? I think that's true of not just safety, but many, many other fields. So one of the things we try to do at Woven is invest in standards and in tools and so on to try to advance the state of the art where for us it seems strategically important. And we do it in a way that's not, obviously a standard is not proprietary when you do it, but also for open source or different projects, right? Where then others can benefit and hopefully spur investment in those things by others as well. So I think that's another aspect where, like when I used to work on LLVM a few years ago, sometimes you would look at new features coming out of C++ in the library or the language, and you'd like to use them, right? But someone's got to implement them before you can use them. And, whose job is it to implement it? Well, the primary people who implement features in LLVM or libc++, they're not selling that to anyone, right? It's just a part of the platform that comes from a variety of companies, right? And so it's nobody's mission to implement new things. So those things don't get implemented unless someone asks for it, right? And I know the folks who are in charge of GCC or MSVC. It's the same thing, right? They only implement things when they get requests for it. And so if you look at it from there's this tool ecosystem and you want to make it better, it's a shared resource, right? Like we all benefit from having these available in our field and in many, many other fields. But we've got to invest in them to make it better, right? Otherwise, we're just waiting for other people to come and make them better for us. And so I think for safety, the same applies, right? Those tools will only be more usable more rapidly in safety contexts if you invest in them. So Misra, for example, it's mostly volunteers on Misra, right, who try to do their best with what they know. But if no one shows up to improve Misra, then it is going to be 10 years behind, right? And then Misra is a standard. You need tools around it to improve. Now, once Misra is out, the tools vendors get people requesting implementations of Misra. It takes it a little bit of time, but it's their job, literally, to implement this, right? So I think there's incentives there, whereas for standards like Misra or C++ or C or so on, there's not that much incentive to do it besides, well, if nobody does it, then it's not going to happen, right? So I think those are kind of two aspects of how I think, yes, the industry lags behind, but it's up to us to set up the incentives to make it better for us and hope that others see like we've helped make that corner of the world better, and so maybe we can all pitch in a bit more. So I think that's part of how I would approach this of, if we don't want to be perpetually behind, then, do something about it.
I guess I have a similar perspective. Perhaps I'm a little bit too far in the weeds here, but like, for me, you also need to know what the cost is to upgrade, right? A lot of times we use a certain safety certified compiler because that's the version that we got from the vendor. But there's nothing stopping us from going out and pulling the latest and greatest whatever stable branch and then doing a diff, and then seeing potentially, here's the changes, here's the impact, and here's what we need to do. So tooling, there's a cost to get it safety certified, right? There's a process that it has to go through. It's expensive. It takes time. And because of the way that process is currently built, people tend to only do this on a particular cycle rather than potentially when there's a minor update, right? And a lot of times we don't even know what the changes are that minor update to that tooling introduces. And therefore, for us to migrate between versions, or for you as someone that has a code base, if you want to migrate between versions, it's a high cost, right? It's a lot of investment. If you haven't invested in the ecosystem properly, your source code literally won't compile when the next safety certified version of the compiler comes out. So you need to stay on top of your technical debt, right? To be frank, you should know what's going on in like the main version of your tools, even if they're not necessarily safety certified. Many years ago at big tech company X, there is a version of Windows that say runs the basis for Azure. That's part of like the fabric. That's what we call it. And then there's a version that we produce that we sell to consumers. And they forked, for lack of a better word. And the effort to migrate the two back together took like 15,000 engineers and 5 years, right? Because the code base had gotten divergent, right? And over time, no one had gone out and said, hey, this change happened. What's the impact here? Google has had similar stories in having to backport fixes to the Linux kernel, right? Because they run on their own special version and eventually it diverges. And we need to think about these things from a safety and from a tooling perspective, right? Obviously, for the software that we write, we are likely pegged to a particular version, but eventually that version will jump ahead several versions. And if we don't know what the changes are, if the compiler has introduced a new flag, if there's a new thing that has come out that impacts us and we are unaware of it, it will be a technical blocker for us to adopt that new feature when that new release comes out. That's a lot of work. That's investment that we as a company have to do, and that's investment that we also need to do to help support the people that maintain these tools, right? We are fortunate at Woven that we have a large automotive code base to work on, and we can say, hey, there's this thing which is coming in the future. It will have these impacts to us. Maybe we can adjust our code base this way, right? Once again, I also second the comments about standards investments. I think this is something crucial that we must do in order to help reduce the time it takes to get a safety certified tool or a safety certified solution in-house, so that way we can be closer to what mainline has rather than a decade behind. I don't know if you want to add anything to that, but like...
No, I agree.
Yeah.
Yeah, thanks for the answer. Speaking of investment, maybe I asked a last comment. So speaking of the investment that we made, we also had a strong collaboration with GitHub and Security to have like an open source tool called QL, which implements the Misra, Konigan, etc. So just wanted to add this as an example of the kind of investment that you can do to move in that direction. Yeah. Yeah, thank you very much for the answer.
Thank you very much for stepping up. Really appreciate it. We have just under 20 minutes left, and I'm happy to call on a couple questions that were really interesting from our end. Would anyone else like to step up before I do so? Happy to hear questions. Yes, please.
Oh, there. Thanks for doing this, first of all. So a subject I'm excited about since I began coding and doing security is about automated bugs detection, basically, how you can write tools to automate specifically security-related bugs. And C++ is usually a place where faster, dynamic tools are used, like AFL. So I'm curious, first of all, here, what kind of tooling have you found in practice that usually gives you the most bang for your money? Like, which tools are good to use for the time they take? And especially if have you tried or using static code analyzers, like dynamic execution engines. I've read that there are some of them, never used them, but I think they are more on the academic side, so I want to know if you guys have the experience in practice and using them and if they are worth it. Thank you.
Sure, I guess I'll take that one. So I'm a huge fan of Clang Tidy, right? I'll be honest. Sometimes the simplest tools are some of the best at finding problems, right? Clang Tidy has a lot of rules that have been developed for it that can find a lot of things. And it's open source, you can contribute to it, it works really well. Although it is technically a linter, it does cover a lot of the most common problems, right? Once again, I think also by properly setting compiler flags, you can also detect a lot of things at the compiler level. A modern compiler is pretty smart, and it knows when you've made a mistake more often than, say, a tool, right? Because the compiler has to put things together, and it will say, hey, there's this thing here that is a mismatch. So make sure you have your compiler flags set properly. Other things I might recommend. So CodeKill has some open source rules. The CW rule pack is open source. You can run it. It does take a while. You have to figure out how to build the particular software, obviously, so it's pretty intensive, but it does pretty good whole program analysis. There's something out there called semgrep. Once again, it's free for use if you're looking for like personal use. It has a set of rules for C++. It's pretty good. It is limited to the file specifically, and it won't catch problems that are more intricate. On the DAS side of the house, I personally do AFL++, right? That and libfuzzer are excellent. They are somewhat time-consuming to set up. The advantage of that there is you can hook up your crash to Ghidra, and you can analyze it automatically, assuming you've got the resources, and you can figure out potentially if you have an exploitable condition, right? If you're looking to bug bounty. I mean, there's a ton of things you can do, right? You can instrument the code, so that way you can determine potentially, where there are bad allocations, right? So this is something that we would do is you basically allocate the memory in a specific way in advance, and you can determine where there's an overrun and underrun, or potentially where you have a leak, right? But these get into things that don't work super well if you have like a static build line, right? I'd recommend you standardize on like a linter, a specific SAS tool, maybe a DAS tool. You write some fuzz tests, and then you go from there.
Yeah, and what I like about static analyzers is using different ones tend to find different issues, right? If you just take the rule sets out of the box, I wouldn't stick to just one. I think all of them do certain things well, and that set of things is not a perfectly overlapping Venn diagram, right? So I would recommend mixing a few to see what they find that differs. I've always found serious things by using a different static analyzer. Even though you might have addressed all the ones from one analyzer, the other ones finds things. CodeQL in particular is interesting. I think it's not as mature as the other ones yet, but I think it's getting very interesting in particular because it does cross-translation unit analysis better than the others. And so if you have a problem between functions or between files, CodeQL tends to find it better than the other ones. I think that's a key difference that's been missing from a lot of tools. The other tools have some things that they do interestingly there, right? I just think CodeQL is more advanced. And I think tools like Clang Tidy and CodeQL allow you to write custom rules fairly easily. So I think that's a really nice way to find either variants. You find one problem here, can I find it somewhere else? Or things specific to your code base, right? Like if you look at Clang Tidy has a bunch of rules for the Fuchsia operating system that are not useful for everyone, but that cater to that specific code base in an interesting way. And you can do that for your code base. So it's a way to supplement the type system that C++ has. Instead of trying to do gymnastics and templates to have a strong type system, if you could just write it in a linter and have the linter figure it out, I think that's a more palatable tool, because then your C++ is easy to read, and the guardrails you can't enforce in this type system that's not amazing as C++ has, you can enforce with a separate tool. I think that's a really interesting thing. Fuzzing I love. One thing that I think would be great as well is when fuzzing is something you run locally on your code base, right? It's got limited breadth. And then testing you do on your own code base as well. But it only finds what you happen to run into locally, right? Real users are great at doing weird stuff and finding stuff that even fuzzers, even though they try to find stuff, aren't great at doing. And so when you can afford it, having checks in production, I think, is useful. Now, how you do this is important, right? Some code bases can just crash and recover. If you can do that, then having a check that just crashes, recovers, but reports the problem is great, because it'll often find stuff that your fuzzer won't find, right? So, for example, if you have like UBSAN turned on in production, there's a mode of UBSAN that's the minimal runtime that'll just report the PC and just a specific problem. You can get the crash report and then find issues that way. There's also, say, things like a probabilistic allocator that will sometimes do retention when you free, right? So something like what ASAN does, you can do in production to, say, 1% of allocations, very small overhead, and if you have a big deployment, will find issues. So that's something that's been done in production in a variety of code bases. I know that iOS has it, Android has it. With a billion-plus install base, you find things that all of your testing will not find. So that's an interesting thing as well. You end up just effectively using sanitizers at scale by doing that in production. So I think there's a lot of interesting stuff that can be done in production that it's more effort, but it gives you a lot of interesting gains as well in terms of bug finding, for security, for safety, or just correctness or whatever else.
Okay, so in practice you use everything depending. There is no tool to fit every case, so you see what fits on every
No, I mean,
scenario.
to be frank, you should use more than one tool, like guaranteed. Like, especially if you have something that is safety critical, right? Man, I'm going to date myself. In like 2005, I think the NSA came out with a study, and they said that you should use at least 3 static analysis tools if you wanted to get 30%, I think, of the bugs in your code for C++. That's 30%.
I think Robert Secord had a study on that when he was at Carnegie Mellon University.
Yeah, because I was talking about it with him, and he's like, oh yeah, I remember that one.
Yeah.
But like, you cannot rely, and you should not rely on a single thing if you have any sort of safety or security critical code base, right? You can't rely on production. You can't rely, because there's like these 1 in a million things that'll happen, like lightning hits the car and a bit flips. What happens to your program, right? But those are a good start to help guarantee. And these are where things like MISRA, like standards, also help, because these standards aim to eliminate undefined behavior, right? Which is something that you don't want in C++, right? They want you to force you to have your code base be predictable, right? Because then you can say, okay, then we can therefore make it safe or secure. And if you have a code base that doesn't meet that, right, or that doesn't have a standard, say it's like a large and diverse ecosystem, then it gets challenging.
Yeah, and what you're saying reminds me, Microsoft in the late 2000s had a paper they published about, they studied Windows crashes, the crashes of Windows itself, the kernel. They get dumps from it, and they would identify when instruction pages had been modified. So a crash that just should not occur, right? Like you know, like Microsoft knows from their code base that the instruction here is an arithmetic instruction, and it crashes with a page fault access or something, right? So it's trying to do a load as an arithmetic instruction or something like that. So they identified pages that are not modifiable and identified symptoms of a bit flip, right? And they had a wide-scale study of, like, in production, what happens, right? I think that was a pretty interesting one, and they could identify different vendors having different rates of problems and things like that. So I think there's a lot of interesting stuff you can do like this. And when I worked on Chrome, we saw a lot of similar things of this is impossible, right? And starting to look for impossible crashes at scale end up giving you clues of how you can make your program more resilient to not just hardware failures, but different types of software failures. So I think that's an interesting aspect as well, like the very wide set of data. And if you instrument it well, it'll give you, clues on how to make things better. Now it's after the facts, right? So it's the type of thing that for safety systems you don't want to be in the business of doing. You want to try to prevent that from happening at all. But in some cases, it's useful to have that in production instrumentation and a variety of means to catch issues if they do happen.
So let me tell a story here. I'm picking on this one particular because of something you said, but Microsoft does the crash dump analysis extremely well, right? I directly worked on that system. If you run Windows Insider builds, thank you. Your telemetry is super valuable for us. It helps us squash a lot of bugs. But for those of you in the security field, in 2008, there's a famous bug, MS-08067, right? Which everybody knows produced the configure worm and was one of the worst bugs in history. That bug was discovered from a crash dump, which this is public on GitHub, so I'm not leaking any information. You can see the write-up on it. But we found egg hunter code in a dump. We were able to determine, as a result of that crash, that someone was exploiting this, and then we're able to determine where that exploit was and eventually issue the fix. That crash dump that exposed MS-08067 was from Japan. It was actually from Tokyo, from a local company. That's about as much as I'm willing to say, because we're on camera. But that was where the first initial reports of that bug being exploited came from here. From unnamed company. Microsoft then determined it and pushed out a fix, and then obviously the rest is history. But like having that instrumentation and that ability to capture that detail after the fact and then analyze it at scale, right? So on Windows, when there's a crash, there's a bucket. That's what we call it, I guess. It goes into something called Watson, which does some analysis up in the cloud. And we can look at billions of crashes every day. And I can tell you that most of them never happen again. So on any given day, there's between like 4 and 20 million Windows users that will experience a blue screen of death. Most of them are not repeatable crashes. Something like 99.999% of them never occur again. And if they do, right, if there's any given point in time, if there's, say, more than 40 bugs that are worth fixing, that's like a Sev0 event. And the entire Windows dev team, we go hands down to fix those bugs, right, from telemetry. But most of them are impossible conditions. You have a bad driver. You have some weird piece of software. Something that occurs that the user obviously has a bad experience, but it's not a reoccurring event. And so that's why these things are hard to find, right? Because like in some of the bugs that we discover, there's very unique conditions for that bug to manifest. And when you think about it, like say you have, I don't know, there was a problem in aerospace, once again, that's public for a while, that like after a certain number of hours flying, a plane's computer would crash because of an overflow. Well, I mean, the solution is you just turn the plane off and turn it on again, right? And that solves the problem. And so we have situations like that we need to account for, bugs like that we need to hunt for. And in C++, this is time intensive, and it's resource intensive, and it's quite a bit of investment. And that's why no one tool will ever meet your need. Especially if they're using something like, nothing against this, but template programming sometimes makes it harder to understand. But on the other hand, it does provide some benefits once you know what's going on in the code base, right? Because then you can react and you can use something like a linter to determine correctness, and therefore you can stop and catch errors earlier on.
That was very interesting, thank you.
Thank you very much. Unfortunately, I think we only have about 2 minutes left, which I don't think is enough time for another question. Immediately following this, we have about an hour of meet and greet. And so please, anything that we didn't get to, feel free, approach the panelists, have a chat. We'd love to interact with everyone here today. So thank you very, very much for coming. We really hope you enjoyed the time that you spent here. I think we'd like to, oh, yes, please, thank you. So I think as we jump into the more informal meet and greet session, we'd like to have a quick kampai to kick this off.
Yeah, so thanks for everyone for coming again. I think last time it was really interesting to have everyone here, maybe November last year, and we got really good feedback. Our goal is really to create like a community and have recurring events, every 2-3 months or something like that. So let us know what you'd want to do, the formats you'd want to talk about or something. I think it's just something that we've been missing here, and finding like-minded people is fun. So please let us know what you'd want to do more, and we'll try to make it happen. So thank you everyone for coming today.